Okay. Can you hear me well? Hello. Good evening or good afternoon. My name is Guillermo Rein. I am professor of fire science here at Imperial College in the Department of Mechanical Engineering. So all of you, welcome. And I'm going to spend the next 30 minutes or so talking about my job, which is fire science. I will start by saying that I am an engineer. All my degrees are in engineering. I first got my first degree in Spain. That explains the accent. I've been told that the grammar is nearly okay. It's just the accent takes a little bit of a time. And then I went to the United States, to California, where I did my PhD. And then I came to the UK about a decade ago, where I became an academic. And first in Edinburgh, in Scotland, and now at Imperial. So what I would like you to take out of this talk today is three things. The first one is I would like you to see the interplay between engineering as a discipline and science, how the two of them interact, of course, in the background of fire safety and fire engineering. The other one would be that you realize the very broad remit that engineers working in fire have to address, the multiple varieties of problems that we have to face. And the third one is that as scientists, that we have all these ways to do science. We have mostly experimental and computational one, and how the two of them answer different questions, and how the two of them actually interact with each other. So these are the three main messages that I would like you to take home today. So first, I will tell you how I started to become a fire scientist. It's not a very specific route. I didn't know about this until I was doing my doctoral studies in California, and I was actually working for NASA to solve the problem of what happens if there is a fire inside a spacecraft. A spacecraft that is with astronauts, where they have to breathe oxygen. They are surrounded by polymers because they're very light and very inexpensive to launch into orbit. And they're full of ignition sources because all these spacecraft have a lot of wiring, and any of them can go wrong. And if they're going to Mars, which takes about 4 years one way, or 5 years one way and back, what happens if they have a fire? And the first question that NASA asked was, how is that fire going to look? And what we saw over the course of that research is that the fire will look very different. In particular, this is an experiment that NASA conducted. It was a little bit expensive to get this photo, but it was a breakthrough. It's on one side is the candle flame that you have all seen, that we can see on a daily basis billions of times around Earth. It's elongated. It's because the hot smoke and the hot gases of the flame prefer to go upwards. The presence of gravity means that gases that are hot are lighter than the surrounding heavier air, and this creates a recirculation current, and then the flames on Earth are elongated. In space, where there is oxygen, like the atmosphere of a spacecraft for astronauts to breathe, there is no such a thing as a preferred direction. The candle doesn't see a preferred direction at all, so actually it becomes spherical. It's just that the sphericity is broken a little bit at the bottom by the presence of the candle itself. So NASA was actually rightly so worried about fires in a spacecraft. In particular, actually, the fires that worry NASA in a spacecraft are actually not with a flame, are the ones that don't have a flame, which are called smoldering fires. Those are actually even more permanent in space. So this is how I became a fire scientist. But some of you might be saying, well, that's a little bit too fast. Let's see, but what are we talking about here? Before I talk about fire, I'll tell you about the physical and chemical phenomena that drives fire, which is combustion. So combustion is a rapid reaction between a fuel and an oxidizer. Here on Earth, our oxidizer, by far, most of the time, is oxygen. There are all the types of oxidizers. And the fuel that most people will refer to are hydrocarbons, being natural, like wood or the forest, or textiles that are actually natural textiles, are hydrocarbons, or synthetic hydrocarbons, namely polymers. So they react, and they will release a large amount of heat, a large amount of energy in the form of heat. It's an exothermic reaction. That is combustion. Although the type of combustion that most of you have experienced is the one that has the shape of a flame. So what is a flame? I'll give you a few seconds to think about this. It's not a straightforward answer. So I'll tell you, if you see a flame, there is over there a flame. A flame is a very thin region of space that actually encloses itself, okay, and create a volume, but in reality it's hollow inside, so the candle flame is hollow. It's just a very thin region of space around. It is thin, so it's a small region of space, and a lot of heat is being released in this small region, which means that it reaches very high temperatures. So high, indeed, that the gas becomes ionized. This is when the electrons actually lose track a little bit of which the nucleus they are going around, and it emits its own light. It is that warm and that hot. Immediately after releasing this energy in the combustion process, very, very quickly, the temperature is so high, they lose it by radiation and convection, and then the temperature very quickly comes down, and then we don't call that gas, flame anymore, we call it a smoke. The smoke is the gas that just a few milliseconds before was a flame. It cooled down, and it was just the product of combustion. Some of you might know Asimov, Isaac Asimov. I'm a fan of Asimov, also because of his work on robots, but mostly because he was extremely wise in actually all physics and technology and sciences on Earth. So he wrote this amazing encyclopedia of science and technology where he himself, by himself, just reviews everything that it was known until 1980s. And he stops at the combustion chapter. And he says, fire is the greatest discovery of humankind. So fire, which we discover, we didn't invent it, fire. Nature has invented fire for us. When we became a species, fire was already raging and doing a lot of things on planet Earth. Actually, when we overcame that fear, when we overcame the fear of the fire, when we stopped running away from wildfires, where our ancestors about 1 million years ago started to maybe play or to be curious about fire, little by little, over the course of thousands of years, we actually end up harnessing that power that nature was showing to us before. And that led to a massive change in civilization. Some people say that actually civilization can happen, not because we are very smart as a species, but because we actually harness fire. It led to cooking, which completely changed the ability that we have to deliver power and to have a diet. It delivered to heating, which means we could live in completely different places. It led to lighting. It means that actually we could do life actually after sunset. And we could also do warfare, for good or for bad, and also all these other processes like metal forming and all the other technologies that led to arts and culture and technology. So that is the bright side of fire. However, remember that fire, before we harness it, was a hazard to us. It is a hazard to many animals. Animals still flee away when a wildfire happens. And unfortunately, we have not been able to remove that problem from our existence on Earth, because we still do not control all types of fires. So we still have a lot of problems with accidental fires, which are by the thousands at the small size and actually by the hundreds on a daily basis at the larger skies. If you look into history, some of these fires were so frightening and they left such a footprint in history that are in the books, and we remember them. One of them is the Great Fire of Alexandria, when the library was probably set on fire by the Romans, and it actually ended up with not only just the library burning, but the whole city of Alexandria. The Great Fire of Rome with Nero, it actually ended up in prose as well, and the Great Fire of London, 1666. I just want to tell you at this point, as a father of 2 kids, that London is the perfect place to be a fire scientist, because although my colleagues at Imperial still don't understand what I do, my kids know perfectly what I do. Papa just makes sure Great Fire of London doesn't happen again. So it's fantastic. So thankful to the educational system in London putting that emphasis in the Great Fire of London. Other fires that you are probably, you should be more concerned about and we're more familiar with are the fires that keep happening in our residential environments. We humans, since we became humans, probably already in our caves, we are surrounded by a flammable environment. I don't want to frighten you, but most of the things that you are looking around right now are actually flammable. Additions to the walls, you are sitting on polyurethane foam, the tables are made of wood, etc. And there is a tendency in humanity to keep adding more and more flammable materials. Different types of materials, some of them are too flammable, and then we correct this and we make them less flammable, but there's always more flammability. Our current houses are very flammable. They're not meant to get on fire. There is a lot of people on a daily basis are called fire safety engineers who make sure that everybody is safe every single day of your life, every single month of the year. But these people are not perfect, and unfortunately accidents happen, and no matter that they try to foresee all possibilities, some of them cannot be catched, and these fires happen even inside living rooms. Also, at this point, I cannot stop myself from bringing you the elephant in the room, which is becoming the lithium-ion batteries. It's a breakthrough technology. It's allowing us to do so many things. It's fantastic. It just comes with all this very fast pace of development of new materials. It comes with an issue we have not been able to address. It's not just that the batteries itself are flammable, which they are. It's that actually themselves carry the ignition source. An ignition source that actually sometimes it just decides to start without warning and without being called upon. And that combination of something that is very flammable and that has a tendency sometimes, maybe a very small fraction of batteries, but there are trillions of batteries on Earth as we speak, means there is an issue. And for scientists, my community, no matter that we are small, we have to deal and resolve this problem. So fire globally, I think at this point I can make a case for you. It is still a problem for humanity. Worldwide, we're talking about 300,000 victims per year dying because of fire. These are the deaths. You multiply that by 100 to get the injuries, and you can calculate the losses, the losses because of fire, the losses because of trying to prevent it, but the losses of also what is lost in the fire is in the trillions on the planet Earth. It's quite a drama. Here in the UK, however, we are, I say probably, although being Spanish I can tell you that it is a fact, we are world leaders in actually keeping our citizens safe. And actually the science and the technology of doing so in the UK is extremely mature. Together with the United States, the two countries that had contributed more to the wisdom of humanity about what fire is. Currently, the record of fire deaths in the UK, pre-Grenfell, is a historical low. It has never, ever been this low. It's a complete trend of decreasing every single year. There is a beep of Grenfell. We're still trying to understand what happened there. It's about 320 people dying per year. That is the same as people that drown because of that die because of drowning, or people that die because of asthma. And so it's not something that we worry in the UK. Although I can tell you that there is a lot of money being put in the government and all private organizations to make sure that this number keeps very low. The bill for the UK of direct and indirect losses for fire is about 7 billion, which are rightly being invested into fighting fires, but also this money could actually be unlocked if we were to do this in a different way and be actually part of the educational budget, for example. So at this point, I've told you something about the science of what is a flame, what is combustion, NASA work, etc. And I'm already transitioning into the engineering one of the engineers who have to resolve this problem. I have this duality. Not many people have this duality. In Imperial, most academics in the engineering department have the duality. We are both engineers and scientists. And no one has ever trained us to deal with this duality, this dual personality that we have. I've dealt with this my own way to learn when I'm an engineer, when I'm a scientist, when I can actually implement one method or the other. So what I can tell you is if I wanted to define engineering for you, we all struggle. No matter that we are experts in engineering, we've been doing engineering for many, many years ourselves, we struggle to define something as large and as human as the endeavor of engineering. Since we started to be humans, we were doing engineering literally 1 second after becoming humans. To the point that if you look around at any point in your life, just look around, and if it's not a rock, and if it's actually not a tree, engineering made it for you at one point or another. That is as profound the footprint of engineering on planet Earth. Another person, I'm not alone in this duality between science and engineering. A very famous professor, Professor von Karman, a rocket scientist himself, an engineer and a scientist, very famous in the era of development of propulsion to space. He himself also went through this duality, and he said it much better than I can say. He says, a scientist seeks to understand what it is. An engineer seeks to create what never was. So a scientist is a very smart person that creates knowledge, something that humanity didn't know before, by looking into, he goes around, so to speak, he or she, and finds something and says, I'm going to study this. The engineer actually cannot do that. The engineer has to come out with something new, didn't exist before, and he does it to come out with trying to solve a problem for society. So at the end, I can say that if science is the best method that we have on Earth to create new knowledge, not the only one, but it's the best that we have, scientific method, engineering is the best approach that we have to solve society problems. It's not the only way to solve society problems, but it's the best. And that is a duality between science and engineering, that if you are in a department, in a research university, in a department of engineering, you have to manage the two of them. So in the case of fire, the science that we develop, the science that all my colleagues around the world are developing, the collective wisdom that has been written in the books that we know about fire, goes into a field of engineering that is called fire protection engineering in the US. In the UK, it's called fire engineering, or actually in other places it might be called fire safety engineering. And these are the engineers who keep us safe, or try to keep us safe on a daily basis. They have a very broad remit. Not only they have to deal with many different types of fires happening in many different types of dwellings, but they actually protect people when they are in the forest and when they are in the building. You probably are more familiar with the protection when the citizens are in the buildings, but we also do protection of the forest itself, so we protect the environment. And if people are in the forest, what is called the wild-urban interface, when the houses are literally surrounded by forest, then actually we have to keep safe the people as well, not just the environment. We do this not just by, so the systematic way of protecting citizens from fire can call upon 6 layers. This can be portrayed as more layers, but actually if you boil them down together, 6 is the minimum number. The first layer, you don't have to, as an engineer, you don't have to call upon all the layers to protect the building. You have to comply with the regulations, but usually what you do is you call for several of these layers. I'll tell you how, for example, the Americans and the British have a different emphasis in different layers. The first layer, the most important one, is prevention, is don't let the fire happen. This layer is breached every single time a fire is reported. But if the fire is not reported, then this layer is working. It's the one that is actually the first layer of protection. But we mean not having the fire happen in the first place. First is don't put the ignition next to the fuel. Remember, we are surrounded by fuel, so the emphasis is on the ignition, because the fuel is going to be everywhere. And the fuel will react with oxygen, and the oxygen on Earth, we have it in the atmosphere. It's given for us for free as citizens of this planet. So the emphasis is on the ignition sources. Make sure that the ignition sources don't find the flammable material, or that no matter that our environments are flammable, that they are less flammable. For example, not all polymers are equally flammable. All of them are flammable one way or another. You can actually modify the chemistry of a polymer to make it less flammable, to make it very little flammable indeed. Or if you are not careful, it will be extremely flammable. The second layer after the fire has happened and there has been a failure in the prevention is make sure we can detect the fire as soon as possible. The earlier, the better by far to make this detection an action to alert people, not only just to alert the fire service, but in particular to learn the people who are in the immediate vicinity of this fire, so they can act upon knowing that there is a fire next to them. The third layer is evacuation. Is you detect the fire to start the evacuation. There are many different ways to evacuate. The complexity of the building escalates with the size or the amount of people who might be inside, but you always have to evacuate one way or another and enable and facilitate the evacuation. The fourth layer is compartmentation. This is a very important layer in the UK. This is the layer that makes the country famous for foreigners because you see all these doors with blue plates saying fire door, keep closed, fire door, keep closed. And foreigners, especially the Americans, have a lot of fun seeing so many doors in the country. That is because of the principle of compartmentation is very important in the UK to keep people safe. And the principle is if the first layer is breached in a compartment, in a room, that's bad. Okay, make sure that it doesn't go to another compartment, not just the fire, but actually the smoke. Because at the end, what really kills first, what really incapacitates people who are trying to evacuate is the smoke. So we compartmentalize to make sure that it doesn't happen, if compartmentation is possible. The fifth layer is what the Americans prefer. Americans don't prefer to put so many doors. They actually have very few doors compared to the UK, but they put sprinklers everywhere. Not just by regulation, it's also a cultural thing. So sprinklers, what they do is they are automatic suppression. You don't need to be there. If you want to see, it's a very simple robot that only senses one thing in the lifetime of this robot is heat. And when it sees a lot of heat, it opens a valve full of water. Hopefully it will be full of water in that moment, and it tries to extinguish or to dampen a fire that might be in the vertical direction of the sprinkler. Also, the fire brigade, the fact that the fire brigade will arrive at some point. The UK are quite quickly, in the US as well. They will also aid into the evacuation and the rescue, but also in the firefighting, the suppression. So the fifth layer is not just the sprinklers, it's also the fire brigades. In the UK or in Europe, in principle, there is no emphasis on suppression, automatic suppression. on the sprinklers, but there is emphasis in the fourth layer, in compartmentation. And that leads to a different environment, in the built environment. The architects that design a tower in London, they end up being different, especially inside, than if a tower is in New York or is in San Francisco. And the last layer is one that is very dramatic when it fails, which is the structural resilience, to make sure that the tower, the building, doesn't collapse. Or if for some reason the engineer and the authorities are going to let this tower collapse in case of fire, for sure it cannot do while there's people still inside. And all these layers require calculations and assumptions and significant knowledge on fire to make sure that these layers actually stay in place, multiple of them, or they are not reached ahead of time. If you think of any recent building fire in your mind, you can actually go and see how many, because the fire has happened, how many of these layers were breached. And very, very often, if the fire has reached you, it reaches us very often. We read and we learn about fires happening on Earth very often. But it has reached the citizens. It means it was in the media. It means it was a big fire, and guarantee that of 6 layers, at least 4, if not 5 or 6, were breached. So now you can try to do that calculation mentally if you want. The same, these layers of protection that we call upon, the same happens in a forest. We also have prevention and detection and evacuation and compartmentation and suppression and structural resilience, not of the forest, but to make sure that the forest can grow back again, where actually ecologists have a very important role. Now that I've hopefully told you about the interplay between science and engineers, and the broad remit of fire safety engineers and scientists, now I will tell you a little bit based on my own experience as an academic and a researcher, how we actually try to understand more fire. So we do this. One of the tools that we use very often is we have a lab. All fire scientists around the world have a lab of different sizes, because ours in South Kensington is a small site. It's fine. We are very happy with it, but it's on the smaller side. These are 2 of my brilliant students, Uji and Eric, conducting an experiment. They have conducted a fire inside that reactor, and they are actually making sure that it's being controlled, and they are looking into particular, in this case, they were looking into the emissions. What typically we do with these experiments is we subject different polymers, being synthetic or natural, and there are thousands of them, to fire. And we see how they react to fire. It's actually called reaction to fire. For example, this over here, you can see is a plate of PMMA about this size. PMMA is a polymer that we have frequently in the built environment, and it's being exposed to very intense heat. And you see the history here on the top of what is happening. At the beginning, it remains just a little bit with bubbles, and then it continues, it starts to darken, and it starts to burn. So what we do is we study that. Not we're just observing, but actually trying to isolate the different variables. This is an experiment that I want to show you very up close. That is a slab of PMMA, transparent PMMA, about this size. Okay? It's put in the reactor, and on top, you don't see it. It's a very intense heat arriving, very, very intense heat. This is going to be the process of pyrolysis. We call it pyrolysis. It's very important in the understanding of fires. Pyrolysis is, as the word means, is that the substance of the polymer is breaking by fire. And it goes from the solid that you see into a gas. And actually, you start to see that the solid is disappearing. The slab of PMMA, after some time, is accelerated by 32 times. I don't want to keep you here waiting for too long, but you can see how the process of pyrolysis is converting the polymer into a gas, and the gas is the one that feeds the flame. Not the solid itself, but the gas. So this step of pyrolysis, converting the solid chemical composition into a different composition in the gas, and this gas being what feeds the flame, is absolutely essential for the fire to find a route to happen itself. If you understand the pyrolysis of the polymer, if you can make a polymer that actually is controlling, reducing, or hindering the pyrolysis process, you are taking a hand on the fire behavior of this polymer. So that's an experiment towards the end. It's about after half an hour of pyrolyzing this sample. We isolated pyrolysis. We didn't want it to ignite. It will have ignited happily, but we put a big effort in not igniting it. And you can see that half of the slab is gone. Where is it? It's in the lab. Well, it was collected in the hood and very cleanly dumped outside after being treated for emissions and everything. But the solid actually ended up in the gas phase in the process of pyrolysis. So what happens is there's a diagram of time at the bottom in seconds and temperature. And that black line is the temperature on the surface of the slab that you just saw. And what happens is, being exposed to heat, the temperature starts to go up. And there is a point where it has heated up so much that it starts the process of pyrolysis. Before that, before our lower temperatures, it was not pyrolyzing yet. It was just warm polymer. Now it's pyrolyzing. It's producing flammable gases just above it. These gases might find an ignition source and ignite. And then you will have a flame on it. And the temperature will continue growing up. If we find a good polymer, a better polymer that has lower flammability behavior, you will see the green curve, which is a polymer that is still flammable, it still heats up, it still might actually end up igniting, but it does it much slower. It ignites later, and it actually might, if you are very lucky, might not be able to ignite unless the ignition source is of a very high magnitude. How do we do this? We actually do this, and we help many manufacturers of composition by understanding all the processes that are involved into pyrolysis. It's a process that is chemically and physically involving heat transfer and many processes together. This is a video that I want to show you of the end result. It's slow motion, so it's the opposite of being accelerated. It's slow motion to make sure that you enjoy this. This is a polymer. Over here is the original sample. It's exposed to a flame. This is a standard that has to be passed if you want your polymer to be close to people. And this one is exactly the same polymer, but it has been treated to be flame retardant. Exactly the same ignition source. This one over here not only ignites very quickly, within a few seconds, not only the fire spreads along the polymer, actually it starts to drip. So the three no possibilities for a polymer to be allowed to be next to people. The other one, which is the same polymer, which acts the same way and it provides the same positive outcomes as a polymer, it actually has been treated for flammability and doesn't ignite, the flame doesn't spread, and it doesn't drip. So it is the art of making, both of them are flammable, but one of them is very difficult to ignite. It's the art of making this. So this is what we do in the lab, in my group, my research group. We have some knowledge of the physics of the process. In particular, as mechanical engineers, we feel very comfortable with thermodynamics, energy flows, and heat transfer, and also the chemistry. Fire has a very extreme component of chemistry. We are engineers. Chemistry will not be our strength, but we do okay. The important thing is that this is not fire, and this is not fire. So we start at the very fundamentals of the processes, and we go up towards the application of the system, and at some point they have to get together. When they get together, that's actually fire of different levels of fundamental understanding. And as we get up, we actually get closer to the actual product, the actual fire behavior that we want to avoid, the one that will be actually affecting the citizens that we have a remit to protect. So the idea is always to be here as engineers, but as scientists, we want to go as deep as we can in the fundamentals. Sometimes you can go very deep, sometimes you cannot go very deep. Sometimes if you go very deep in the fundamentals, you lose track of what you were doing, what you're trying to do to begin with, which is really to understand how fire behavior happens so you can avoid it. Another example of the research that we do is experimental, but it's not inside the lab. This one we get out of the lab. This is something that we learned after September 11 in 2001 in New York. The terrorists crashed airplanes into two of the towers of New York, and the towers sustained the impact of the airplanes. What the towers did not sustain was, and Bin Laden didn't know this, is that the fires that started with the crash were actually of a very large magnitude, much larger than anything that any engineer had ever considered, not just in the design, but actually even possible. These were about 100 to 1,000 times bigger fires that engineers are asked to protect against. And the towers were brought down. What we discover later on is not that the towers were brought down because the fire was actually that large, as I just mentioned. It was actually specifically because the behavior of those fires that we saw, millions of us saw it, probably you actually saw it in real time in TV, was not the behavior that the engineers are asked to consider. Those fires were behaving in a different way. They were actually what we call traveling. They were moving along a very open plan office. If you ask the engineers of that time, or even now, how they're asked to design things, they cannot assume that the fire travels. They have to assume that the fire is engulfing the whole enclosure at the same time, what is called flashover. And the structural engineers considered that there is an assumption that that is the worst case scenario. But this is not what happened in the World Trade Center, and the towers actually fell down. So we did this experiment. We just saw it. It's an experiment in an abandoned farm in Poland. That's why it looks like it doesn't look like an experiment, is we had to go to Poland because to do this experiment, it was very difficult to do otherwise in terms of permits of safety and pollution. And it actually remains, we did it last year, the largest fire experiment ever conducted. I'm not particularly proud of this because I think that it took me a long time to arrive to this field. This field has been developing since Second World War. And it's a little bit a shame of my colleagues that they have to wait for us to do an experiment of this size. What we saw in this experiment is that the fire was traveling, something that you have seen probably in the forest, but something that the structural engineers have never been asked to consider. And that actually ends up affecting the structure in a different way. And for some structures and for some fires, it's actually worse a traveling fire than a fire that is actually homogeneous. This actually then we brought it into computer codes, computer models, state of the art of how we compute the structural response of a building. You are seeing a multi-story frame made of steel. And in the third floor over here, there is a fire that is traveling in this direction. It's traveling very slowly. It's accelerated for you. It's already about 100 minutes of fire that has been happening. And you can see the little arrows that you see are the forces that develop in the columns and in the beams of the structure. And the little curves that you see that are growing is the deformation that the structure sees, exaggerated deformation. So this type of work, this type of research allows actually engineers to truly understand what is the effect of their assumptions in the results that they are trying to do, because they have the remit of protecting the structure in case of fire. I'm happy to say that not only I'm an academic in my ivory tower, doing things that are fantastically fun, but sometimes we come down from the ivory tower and really happy to be able to say that the work that I just saw, the work on traveling fires, was inspired from what we saw in the World Trade Center. Thanks to working with engineers, had ended up actually being embodied one way or another in about, now probably it's about 40 or 50 buildings. All of them are iconic buildings. And they used to be in London, now they are all over England, even in Scotland as well. Canada is doing this, and the Middle East is doing this. And it's a way of designing which is different than the way of designing that we had before. It's spreading quite significantly, which is quite nice. Especially, for example, my son Alexander and I really like Battersea. So the firemen of Battersea actually consider traveling fires inside. And I can go now back to bed and say I did something meaningful when I can look at Battersea and think that the bolts somehow are differently located because of traveling fires. It's not only just about the buildings. We also work a little bit in the forest. We do experiments where we look into how biomass burns, how biomass, being in the trees, in the leaves, or biomass that we humans produce burns. You can see that the chemistry is quite rich. This is the biomass originally, and as you move upwards, the biomass has been subjected to intense heat. It actually at some point has char over here, and then the char actually has reacted. And at the very top, you have the ash. And the fire is a process where the biomass initially looks like this and ends up in absolutely just ash. And ash is what is the content of the biomass that cannot burn. It is actually impossible to make it react. It's the mineral fraction of it, and that's the ash. So we do a lot of experiments with the type of fires. This is, for example, an experiment where we have an infrared camera looking into the sample from the top. We ignite in the center, and you can see there is nothing in this fire over here. This has to spread radially, and you have a leading edge over here, and you have the center, what we call the burnout, or the trailing edge. And we can study perfectly the spread rates of the leading edge. We can see the forms. If you put wind on this, you can see the different effect of the winds and how the fire goes in one direction or in the other. And also, actually, it's allowing us to develop technologies to detect these fires. If we can detect this in the lab with our infrared, maybe the satellites or drones or helicopters can also detect these fires the way we do. And early warning systems is always very beneficial. We combine these, for example, with computational models. There has been an emphasis today on experiments, but it will be the second model that I mentioned. This, for example, over here, this tree that is hanging in the air is a tree where a fire, a smoldering fire, has actually consumed over the course of 2 weeks the soil that sustains the fire. So that's not a funny tree. It's a tree that has lost about 1 meter of its sustaining soil because the soil is flammable. The soil has high organic content, typically peat. And the fire, without its flame, it has actually burned it over the course of a few days. These type of fires, we actually simulate them in my group. We have computer models that are able to tell us to predict the temperature the temperature and the velocity at which the fire is propagating, and also if you look over here, the very rich chemistry. Each of those curves, I don't go into the details, is a different chemical reaction happening, and the interplay of all these chemical reactions actually ends up with the temperature and the fire that you see at the top, which is very important to be able to have very small experiments here in South Kensington, the most expensive neighborhood of Europe. But then you have an experiment, a computer model that is able to replicate and extract knowledge from the small scale experiments, and then we use the model to explain what is happening in the field scale, this being a building or actually a forest that is burning. And that's a methodology that is called upscaling. We call it upscaling. We feel very comfortable doing it, a lot of experiments, very detailed with state-of-the-art computer models. And the last one is emissions. This is actually peat, it's a smoldering. You don't see a flame, but this is a fire. Just below this layer of peat that you see, the smoke is coming from a fire that is happening underground. In the lab, it's a very small thing, and it's funny. It looks like a barbecue. But when this happens in nature, it leads to the largest fires on Earth. You cannot see the source of these fires. These are the peat fires of Indonesia and Malaysia, especially in the island of Borneo, because the cloud is literally on top of it. This cloud has been formed over the course of 2 months of continuous large-scale fires, not just one fire. We're talking about thousands of fires. These clouds of emissions are not very buoyant. It's not flaming, which is very buoyant, and it will immediately go into the upper atmosphere. It actually stays attached to the floor, forming layers maybe of 200 meters, where animals and people actually live at the mercy of the wind. So this is actually the worst case scenario in terms of emissions, because they don't get away from us. They stay with us. This cloud over here, it happened in 1997. It was a particularly really bad one. Not only NASA satellites could see it, which is already quite something, is that actually the cloud reached China and it reached Australia. And it was the first time in history that it was an international dispute about trans-haze, or what is called trans-pollution, trans-boundary pollution. China and Australia were not happy that actually Indonesia and Malaysia were not dealing with their fires, but they were actually dealing with the consequences. And since now, in diplomacy, actually there is the concept of actually transboundary pollution, and it was actually started because of these fires. Also, the footprint of these fires is enormous. It's about 10 to 20% of the equivalent of anthropogenic emissions. And if you want to know how much that is about the whole footprint of Europe, the European Union, has a footprint of these fires that happen on average every 3 years, or the whole worldwide fleet of cars. All the cars on Earth, which for media are always the emphasis on carbon footprint, that is about the footprint of these absolutely massive fires that happen in Indonesia. So we want to help. One of the things that we do, the other photo that you saw of Eric and Uji doing an experiment, they were collecting the emissions, and this is actually the emissions that we collected. It's in a microscope. This is half a micron. So it's a really high magnification level. Don't look into the blobs. The big blobs is just the media that we use to collect the samples. The smoke, the particles that people in Indonesia and Singapore breathe, are actually these amalgamations over here, and are frightening. It's not just about what it is. We are fascinated to know which is this carbon, brown carbon, black carbon. It doesn't matter at this level. Look the size. Doctors are very concerned about the size of particles. They are so small, they are smaller than 2.5 microns. They can actually go well into our lungs and actually into our blood system, and they are small enough that actually can actually permeate into the brain membrane. So this is definitely something that cannot, the human body and the living organisms were not designed to breathe these in large quantities. And the last thing that I want to finish with is not only that we do science and we pass this to engineers to protect citizens, we also do something that is very important in academia, which is teaching. And maybe this talk that I'm giving is part of this. This is when we actually use our knowledge to pass this to the collective wisdom of humanity through the specific way of actually talking and giving lectures and creating courses and textbooks. And in particular, in my department of mechanical engineering, to be involved into creating, shaping the next generation of engineers, in particular for Imperial, which they are pretty smart, is the most rewarding activity that we do. So I'm concluding just saying fire it's not me saying it, it was Asimov, is the greatest discovery of humankind, but before we discover it and even after we discover it, remains a hazard, unchecked, and quite dangerous. That fire science and engineering, these are the two disciplines, one creating knowledge, one creating solutions to the problem, that work together to protect citizens, they protect our lives, they protect our properties, and they protect our environment. There is a remit as well to protect the forest and the planet and the climate even. So we do the safer world, and that we we, in particular as a scientist, I can tell you the role of developing understanding, research, and passing these to the engineers to develop solutions for us is absolutely essential. The engineer cannot wait for the scientist to deliver knowledge. The engineer will provide a solution no matter what. But if we can provide more knowledge to the engineers, they will actually come up with solutions with more knowledge. Okay? So the engineer always appreciates us creating knowledge as fast as possible, and they will decide which bits are used and when. And the last one is a call for help. We always need help at different levels. Of course, you should consider a career change or a new career in fire safety engineering or in fire science. You can collaborate with us at Imperial. You can collaborate with any fire lab that you might know in the place where you are, or just support us different ways by reading and communicating with us. So with this I finish. Of course, I will not be here at all if nowhere to be for my students and my researchers. So a big thanks for them, and as well, which is equally important, to our sponsors, which at the end they believe in us and gave us a significant amount of money. Hopefully we did something useful with this. Thank you very much. And if you have questions, I know I went a little bit over time, so to speak, but if you have questions, I'll be happy to answer them. You talked about 6 ways of stopping fire and preventing it, but you're just focusing on the forest fires. Is there not a case sometimes where actually that's a good thing, and obviously some of the plants have evolved to live with the fire, and actually suppressing it might cause problems in the future? So how do you balance all of those things? Awesome question, fantastic, because otherwise I would not find the time to do it, so now I can do it. That is true, and that actually is a game changer. All fires in the built environment are bad. No fire whatsoever is allowed, period, end of the question. In the forest, the situation is quite tricky, because actually fire was developed before humanity. They would not be life on Earth if it were not to be for fires. They actually close the oxygen cycle and the carbon cycle. So we better not get rid of fire, because we will get rid of planet Earth. And it's true that we cannot suppress or modify all forest fires. The level of knowledge in the forest is even higher, what is required, because now you need to know if you want to suppress it or not, or how you want to suppress it or not. The Americans have run into a really big problem, because for the last 100 years, they've been really good at suppressing everything, every fire that moves. And what they have discovered, and now there is enough data to conclude on this, is the more they suppress, the bigger the fires become. Other countries, we have not been able, not even dream of suppressing all fires or mostly all fires. They continue having the same problem. So the Americans are teaching us, all of us, that we cannot suppress all fires, because nature reacts to this in a way that is actually making the situation even worse. So thank you. And it's not straightforward to know which fires you can suppress and which ones not. We are learning this as we speak, hopefully with the role of science.
Thank you, very interesting talk. I live near Grenfell. You mentioned Grenfell. Will you be having any input into the investigation on the Grenfell town?
Yeah, the situation is such that every single fire scientist and fire engineer in the country is involved in Grenfell. Literally, the whole community, we are not very large, but the whole of it is engaged into making sure that this tragedy, which is very dramatic, becomes somehow a force for the good. It will take time. I'm particularly involved officially in the Grenfell inquiry, but even when I'm not involved in the inquiry, I am also, as a scientist, a member of the community trying to address the problem. What I can tell you is what we are seeing that is happening in Grenfell is not just particular of that building, it's not just London, it's not just UK. This is a worldwide problem. It has happened before, but not all the countries have reacted the way the UK is reacting. What we hope is this will be solved for once by the UK for the rest of the world. And then probably actually we might even benefit by exporting the solutions of we learn how to solve this. It's not a trivial problem. It's a tragedy. It should not have happened. It's absolutely horrible. But it's a problem that as we speak, many other countries in the world continue having. Some of them are on denial that they have it, which is even worse.
Really, following on from that point, I'd like to ask a question around the institutionalization of the fire safety industry. So if we go to the Grenfell case, and before the Grenfell disaster, BRE, the Building Research Establishment, were asked by the Department for Communities and Local Government to assess the risks of building cladding. I'm sure you know this. And BRE did a number of trials, and they concluded in their reports that the danger of fire from cladding was very low. They did tests those tests with the materials they used showed that the dangers were very low. Something clearly went wrong.
A lot of things went wrong.
The imagination of the people involved, the framing of the problem. Do you have any thoughts about?
I will not get into the root. It will take me about 10 years to answer your question.
Right.
Actually, no one can answer your question. It's a good question. What I can tell you is everybody should be engaged into answering this question. We cannot answer it yet. What I can tell you is, unfortunately, we know very little about fire. The complexity of fire, some of our founding fathers said, fire is as complex as the human body. Now, think about how many million doctors, and doctors are really smart people, I'm married to one of them, how many millions of doctors are dealing with understanding the human body, and how many of us, fire scientists, are actually trying to understand the same phenomena. So there is a lot about fire that we don't know, but we have the remedy to keep citizens safe. So it's quite difficult. At the end, most of the decisions are not being taken by us, fire engineers. The decisions are taken by someone else. There are so many people involved in the building of a building that at the end, it's not, if we will give you bunkers, right? I don't know if you want to live in a bunker, but we will give you bunkers. We'll give you a structure that cannot burn, that cannot fall. The fire can actually not breach compartmentation, but maybe no one will be buying our bunkers. So what I want to say about this is that we are learning to answer this question. Grenfell is one of these events that actually will accelerate our process to answer these questions. As the World Trade Center collapse of the 5 towers, actually also in my community led to a blip in the amount of knowledge that came out right after that. And it happens every single time there is a massive, in engineering we know this, it's called design by disaster. I know citizens are horrified by this, but it's a fact of engineering, and engineering belongs to humanity. After that tragedy, everybody puts way more emphasis into understanding how can we avoid this from happening, which the day before, the emphasis was not there. But I would prefer not to go into the details of that question, which is really good, but maybe in 10 years we meet for a coffee and we'll answer.
If I came to you and said, I have unlimited funds, I want you to design me a house that is completely fire safe, what systems and materials would you put in place to do that?
But you still want it to be comfortable and look good. Unlimited sources of funding, that's really good. Unlimited sources of funding for an engineer is amazing because it means... So actually, you know what? I would probably be giving you something very similar to the spacecraft of NASA. NASA has no problem with budgets. Their budget is known to be, especially in the 80s, to be literally almost unlimited. And they put a lot of smart people into making sure that astronauts were not going to die in a spacecraft. And I don't know if you know this, but actually 3 astronauts died because of fire in the Apollo launch, Apollo 1, I think it was. But that's it. No one else has died because of fire, and they have had fires in the past. So I will give you something that feels like a spacecraft. I don't know if you want to live in a spacecraft.
My grandchildren will love it.
Any other question over there?
I noticed that you've got an ERC logo on your funding. I just wondered what you, as an academic, thought, if you've got any concerns, obviously, as we as a country lead the EU, will you, as a department, think you will feel any impact on the sort of cross-European research into your particular field?
So I'm from Spain. I marry a French German. Our kids are British. And I thrive in international collaborations. So I am trying to understand what is happening with Brexit, but I'm extremely respectful that the country has decided to do this, and I am here to help the best I can do. If you ask me, I would prefer not to have to help, because I would prefer it not to happen, but I'm here to help, and we will make this a force for the good.
But in your field of work, in fire safety and fire regulation, do you feel like it will have an impact?
It is a game
Governed by EU fire, for example.
It requires a reorganization of the funding flows, that's for sure. The UK is not short of research money, but what we might miss, and ERC is an example for this, it's not just the amount of money, is the quality of the money. ERC is known, I'm happy to be able to tell you this because I got one of them. It's not just that it gives you a lot of money, it's the quality of the money that comes with it. The process of international competition with the best of Europe that actually end up with this proposal to be as good as end up being. This is something that is not just the money that you give, it's that you extract the best out of your scientists. And that might require just more than reorganization of flows, might require maybe actually never leaving ERC and being still involved in ERC. But obviously, the research community in Europe, or actually in the world, are very concerned about Brexit. And of course, there are different sections of the country where Brexit supporters are in different quantities. I've never seen in academia, or at least not publicly, a supporter of Brexit, because they all know the amount of work that it's going to get things just back to the level that it was. And for us in academia, there is no benefit with Brexit. So trade, they say there is a benefit. Immigration, they say there is a benefit. For research, there is no benefit whatsoever.
At the World Trade Center, there was a third building that...
Two more. Three more.
Have you looked at there is controversy on the reasons why, because these buildings were not hit by the planes, so they didn't create so much heat, but they collapsed.
Yeah. Yeah, indeed. Actually, more. It was learned more by, I think it's Tower 5, World Trade Center 5. It is a tower that collapsed. It was much shorter than the Twin Towers, so people don't know about this. But it also collapsed, and no airplane had hit it. And this one was actually just because of fire, but it was actually ignited by the debris falling from the other towers. And we actually learned more about the actual structural response of a building in case of fire from Tower 5 than actually what we learned from Tower 1 and Tower 2. So yeah, we definitely have to look into this. It is, for us, is the opening of a new way of doing foreign structures, the fact that Tower 5 existed. Because for a really long time after World Trade Center, I looked this, World Trade Center happened, you can all probably remember where you were. I was actually in California. It was the second month of my PhD. They called me from Spain, they said, wake up, look into TV, and I watched this in TV. And I can tell you, since then on, my community has always been talking about the World Trade Center and how it has been changing. And for about 3 years, it was all about the impact of the airplanes. The towers collapsed because of the impact, the mechanical impact, the fact that the airplanes had actually sheared and cut all these columns and had created this absolutely massive blast. But little by little, it started to say, it's like, I'm sorry, but engineers and scientists cannot explain this collapse only based on the structural response. And then in Tower 5, we said, when we discovered that Tower 5 was happening, we said, well, this one is not that it has a component of the airplane crashing and damaging it structurally. It's actually that it had no structure. And then traveling fires actually was born more of that type of behavior that we saw in Tower 5. Any other question? It's a trade secret. First, I didn't do it. This one in particular, that's not. I'm happy to say. If you are not careful with the chemistry, for me, I'm not a chemist, right? Sorry for the chemist. For me, flame retardancy on a chemical pathway is almost like you put these magical powders. They're always very small. They're always very special, but they have a very powerful effect. So depending on the powders that you put, you might have secondary effects. I said it's true. Some of this chemistry is so powerful that not only they stop fire, but actually might stop other types of reactions. In particular, I can tell you this case is a trade secret. I didn't select it. I was just asked to look into the behavior. And the people who took the decision were very careful to make sure that this was environmentally sustainable and no health hazard whatsoever. And they were very happy to see, thanks to us, that also it was so effective in making the polymer not flammable. Good. Well then, thank you very much for coming. Hopefully you enjoy it.